Because the review, we've got to cover a little bit from old clear up through the new. So when the driver first steps in the car, sits down, we can have either manual or power assist brakes. If it is power assist, our brake pedal is going to be somewhere around 3-to-1 for mechanical advantage. So if you put 50 pounds, that's 150. If it is not power assist, it's going to be about 5-to-1. So the same 50 pounds will be 250. Going to be multiplied 5 times. So we have the multiplication in our pedal. The pedal pushes a push rod that comes right through the back here. That push rod is critical to set the distance that the master cylinder moves. If the push rod is too long, some of them are adjustable. If the push rod is too long, it won't release all the way and you'll build pressure in your brake systems, can burn the front brakes up. If it's too short, then when you step on the brakes, the pedal has to move too far. Remember, we got that long mechanical advantage. And so if it's 1/8 of an inch here, it's going to equal about 2 inches of pedal movement down here because of the difference in length. And so we need to make sure the push rod is the correct length. We did one of these last week where the guy didn't have hardly any brakes and the push rod was wrong. Okay, next thing is the booster. The booster helps us multiply our pressure. These are called the vacuum assist, which means that it has a diaphragm that hangs here and it's got vacuum on both sides. As long as the vacuum is equal, it doesn't do anything, it just sits there. When we step on the brake, we actually vent the vacuum out of the back side, or let atmospheric pressure in. And when we create a difference in pressure, the higher pressure against the lower pressure is going to help push. The harder we step on the brake, the more air it lets in and the harder it pushes, and that's how we get our mechanical advantage. So on the booster, when you check to see if the booster is functioning correctly, you climb in and you pump the brakes several times until the boost is gone. Make sure the pedal is fairly hard and keep your foot there and start the vehicle. When you start the vehicle, it should pull it down about 3/4 of an inch. Okay, you're going to feel that. That is a good test for the brake booster. If it doesn't do that, then you have a bad booster. Okay, that's a good test for one. All right, now we're out here to the master cylinder. Any questions on the booster?
That's different than a hydro boost, right?
Yeah, the hydro boost uses hydraulic pressure from the power steering pump. This uses vacuum.
Okay.
I ought to mention too, right here, we have a check valve. This check valve is designed to keep vacuum in the booster once it's in there. When you drive the vehicle, the further you step on the gas, the lower the vacuum drops. So if you're climbing a steep hill and you're stepping on the gas, you may drop to like 3 inches of vacuum. Well, you don't want to lose all your power assist. So it's going to maintain that vacuum in here to compensate for the loss of vacuum here. It's also a safety. If your engine were to die and it completely quit running, your booster will have enough vacuum to give you power assist for usually about 3 brake applications. Okay, and so that check valve can go bad. Now we're to the master cylinder. Master cylinder, starting in 1967, they went from a single piston to run all the brakes to 2 pistons in there. They did that because if you had a brake line or lost a brake line or something like that on the early systems, you lost everything, you had nothing. This system, where we have 2 pistons, if you break a brake line, the other half will still work. Now, we started sending from the master cylinder. There's 2 lines because there's 2 pressure ports on this. One of them, when they first started, went to the front brakes, and the other one went to the rear brakes. So we had what we call the front-rear split. And if you lost one half, it would be the rear or the front. Since the front brakes, another theory thing to remember, front brakes do approximately 70% of all of your braking.
Yes.
Okay, because they require, or they do so much of the braking, people became concerned, the engineers, and they went to what's called the diagonal split, which means that one of these is going to go to the left front and the right rear. The other half is going to go to the right front and the left rear. So if you lose braking, you have one from each side, and you have one of them as a front brake, so you have a lot better braking. It's going to pull a little bit to one side because the front grabs harder than the rear, but you have increased braking. On these systems, if you were to lose, if you had a front rear split and you lost your front brakes, that means you're down to 30% braking. And if you had a load or you're carrying something, I mean, you'd step on that with both feet, you couldn't stop the vehicle. I mean, hardly at all, which is part of the reason they changed that. Now, to go to from a front rear split to a diagonal split required him to do something different here. If we did both with the front, then we could take one line out and go to both front. We could take one out of the back and go to both rear. When we went to a diagonal split, we had to have on each half, one went to the front and one to the rear. That means that there's 4 lines on this instead of 2 now. One in front, or 2 in front and 2 behind. Okay, for the diagonal split. Does that make sense? Mm-hmm. Okay, so if you look and you have 4 lines, that tells you have a diagonal split. If you only have 2, it's generally front rear. Okay? Another thing, when you look at the master cylinder, most of them will have 2 different compartments in the reservoir. And one of them is going to be quite a bit bigger and hold more fluid than the other one on a front rear split. Because on the rear brakes, we send the brake fluid back to the shoes. They expand out when we let off. The springs pull them back and push all the fluid back up the master cylinder. On the front brakes, as the pads wear, the piston keeps pushing further and further out. And as it does, it has to fill in with brake fluid behind it. So if you have a piston this big around, one on each side, and it moves a quarter of an inch, that's a lot of fluid. So we have to have a bigger reservoir for the front and for the rear. Then we need to look at the fluid. In the fluids we have .3, .4, .5, and .5.1.
And dot 3 and 4.
Yeah, and there's different combinations of those. Some of them, we have synthetics and whatever, and they'll tell you different things. But basically, those are the ones.
And you know we can mix all of them. Huh?
No.
I had to give you that.
We can mix all of them, but
Dot 5.
dot 5 is silicone base. It's a different base. 5.1, 3, and 4 are the same base, and they can be mixed. I prefer not to because they have a different boiling characteristic, but you can if you need to. Okay. Now, as we start to leave the master cylinder, you guys okay with doing this a step at a time like this? Mm-hmm. As we start to leave the master cylinder, we have to have something to tell the driver if we have a problem. So we're going to take the pressure from one half of this and put on this side, and the pressure from the other half and put on this side, and it's going to tell us a difference in pressure between those 2 pistons in the master cylinder. It's called a pressure differential switch, or a difference in pressure. And when you step on it, it has to have the ability to shuttle back and forth a little bit because your brakes aren't always in perfect adjustment. But if we were to lose pressure on either one or the other side, when you apply it and when I have pressure on this side and not this one, it's going to scoop that valve over, close the switch, turn the light on the dash on. Okay, it's going to tell you have a problem. And it doesn't matter which side. So if the light on the dash comes on and stays on, that's one thing that can cause it. Okay, there's more than one thing that will cause it, but that will turn the light on, telling you got a problem with pressure. Now on that switch, it tells us difference in pressure. Some manufacturers put a spring on each side of that, so if you step on the brake and we don't have pressure on one side, it slides over, turns the light on, you let off the brake, Now the spring pushes it back and equalizes and the light goes out.
Yeah.
There are others that don't put a spring in. So once you push that valve over and turn the light on, it stays on. On those systems, we have to create a difference in pressure on the other side to move the valve back and turn the light off. And when you do that, you need to have a partner that you're working with that paying attention and not looking around like this, because if you create low pressure on this side and it shuttles back and goes off and back on and they're not looking, all they know is the light's still on. Pretty soon you lose track where you're at. And there's been many cases where people just get frustrated and put a whole new valve on there to fix it.
Oh, I was going to say, you seem like you've done experience before.
Yeah, I've experienced that. Okay.
Where are you working with us?
Okay, so that's the pressure differential switch right there. Now, we're going to start with the front, on a front-rear split. We leave the master cylinder, we go past the pressure differential switch, it comes and it goes to both front brakes. Now the front brakes are a disc brake starting in 67, and they ride almost zero clearance. Okay, I've got one loose, you can see. We're going to look at it here in just a minute. The back brakes on the early systems were a drum system, and they have to be adjusted out on both sides. Not just one. Anyhow, if it's not, then when we step on the brakes, the brake fluid from going to the back has to move the shoes out to contact the drum. If they have to move too far, the pedal's going to sink close to the floor while it's trying to push them out to apply. Okay, one of the ways we can find that, if the pedal goes almost to the floor or near the floor, when we pump the brakes 3 or 4 times and it pumps up, that means that we're moving more fluid back there, and now our pedal's where it's supposed to be. So we check for adjustment in the rear brakes. So
That's when you pull the brake.
one of the things I asked you to do. Another thing is we check the parking brake to see.
Count.
Okay. All right. Now, since the drum brakes have to move out to apply, and the disc brakes are zero clearance, that means when we step on the brakes and start to move fluid, the front's going to apply just like that, while the back have to move out, especially if they're very far out of adjustment. So because of that, as engineers, we need to delay the application of the front brakes to give the back brakes a chance to apply.
That's called the meter.
That is called a metering valve, where we meter or measure how much fluid is going to the front brakes, but we slow that down to allow the back brakes time to catch up. The metering valve is only used on the front brakes, and it's only used on drum in back, disc in front. If we have 4 discs, we don't need to do that application, all the same. Okay, so now we have the front half of the brake system. After we get past the metering valve, we go through the lines, and we got to have some kind of a flexible hose to allow the wheels to turn and to move up and down. Okay, that hose, when it starts to fail, will fail from the inside. And since it is black, when it starts to fail, we let up on the fluid and it will graduate. It'll gradually move back up the line to the master cylinder and turn the fluid
Black.
black. Okay. When the fluid is black, it'll actually start to put sludge in the bottom of the master cylinder. You can find that sometimes a 1/4 inch deep. And that is lining from your brake hoses. And they break down from the inside. They'll crack from the outside, but they break down more from the inside. So there's another thing with our fluid. Okay? Now we're out to the caliper, and the caliper over here, we have a piston about this big around, and around the caliper between the body and the piston, we have a square cut seal. We call it an O-ring, but it's a square cut O-ring. When we apply the brakes, that piston pushes through that seal to apply the brakes, and that seal will flex a little bit. And as it flexes like this to allow the piston to push through, we apply the brakes, and when we release, that square cut seal returns back, and that's what returns the piston. Okay, that's the release on the disc brakes. And it doesn't have very much movement. That's why we're almost at zero clearance. The next step the manufacturers did, since the brake pads were dragging a little bit on the rotors, that's costing mileage. So they came up with a low drag caliper. They made a little bit different square cut seal, and inside the caliper body, instead of being square like this, they angled one side over so the seal could flex further. Yeah, it's a low resistance. Now when we step on it, the caliper pushes in and that seal can flex a little further. When we let off, that means it's going to pull back further and relax the piston so the pads don't pull on the rotor. And just that loss in drag will give you 2 or 3 miles per gallon better mileage. So you can see why people started doing it. All the manufacturers climbed on board, because if I didn't do it and you did and everything else is equal, you're getting 2 miles per gallon better than I am. That's a big selling point. Well, basically everybody did. Okay, it's called a low drag piston. All right.
Low drag caliper?
Yeah, low drag caliper.
So then there's technically 3 kinds of calipers, right? We've got the floating, the one that doesn't move, and then the low drag.
Floating, the static, and the load.
Yeah, we have a sliding, a floating, and a fixed.
Fix. Okay.
All right. In conjunction with this, now if the piston returns further, that means that it has to push further to apply, right? So now we have to have, that gave us another problem, we have to have more fluid to push the piston further. When that occurred, we changed the master cylinder, and we designed, or they designed, what they call a quick take-up master cylinder. On a quick take-up master cylinder, because we have to move more fluid now to the front brakes, right? Because it releases further. They put a bigger piston in the back half than the piston that applies the pressure. So now when we move the fluid, the bigger piston is going to move more than the smaller one, right? And as we move it, this one moves more fluid than the other, and it pushes it past the lip seal in the front. So now we're actually moving fluid from here into the front of this. That gives us more fluid in the front of that piston, right? And as soon as that starts to apply and build pressure, it opens the valve in the master cylinder, and now the extra fluid that bigger piston pushes goes back up in the master cylinder. That little valve in the top of the quick take-up master cylinder is designed to work somewhere around 60 to 100 psi, which means all the fluid that it moves goes in front of this piston until it reaches that preset, and then it goes up in the master cylinder. Okay. Now tell me what's going to happen if that valve goes bad and doesn't hold pressure.
It's gonna blow his seal.
It's just going to all go to the master cylinder.
That's right. If it doesn't hold pressure up to that 60 psi, it's not going to force it to go past that front seal and put more in front of there, right? It's going to go the easiest place to go, and if the easiest place to go is up in the reservoir instead of in front of that seal, now you don't have the extra fluid in front, so your pedal's going to drop almost to the floor, way too far. Your brakes are going to be good other than that, so if you have a pedal that drops too far, you're back to the master cylinder because you have a low drag piston or caliper. Okay, did that make sense? You okay with that? Okay, so we've got.
We're looking for that on the test. They're going to word it crazy.
You've got that. There will be some questions on that on the test. I'm positive. I don't get to see the test, but I'm pretty sure it'll be there. Okay, so we're okay with the fronts to this point. And we've gone over a regular master cylinder, a quick take-up master cylinder, a caliper, and a low drag caliper. All right, now we're going to take the fluid back to the back. We're going to start with the old drum brake system. The fluid is going to go out one line and split and go to both rear wheels. We also have to have a flexible line on the back because we run the lines on the body, but the rear end, the differential is moving up and down and whatever, so we have to have a flexible line. It'll do the same as on the front. So we have a flexible line for the front, one on each front and one for the back.
And mine went.
Okay, on these systems. All right, now on the back, we take the fluid and move it to the back, and we go out to the wheel cylinder. The wheel cylinders are going to create pressure depending on the size of the piston. If we have 100 pounds pressure on a half-inch piston, it's going to push 50. 100 pounds on a 1-inch piston, 100. 1.5 inch, 150. Okay, so we can control the pressure that way. Now we come to the drum brakes. The drum brakes I have one over here. Let me show you right here. Okay, we've got two shoes on the drum brake. The piston pushes these out. We can have several different designs for this. This one is not a dual servo. Okay, on a dual servo, this piston pushes out like this. As soon as both shoes touch the drum and create friction, we're going to try and rotate with the drum. And so this is going to push out like this, and then the whole thing is going to slide over until this hits the stop up here. Now on a servo, that means one piston or one half of this serves the other half to help it work better. That's why it's called a servo. So on those, the pressure from this shoe, or the friction from this shoe, is going to try and turn with the drum, and it's going to push straight across to the bottom of this shoe, and it's going to be locked in at the top. So this shoe's job is to apply pressure to this shoe, which does most of the braking. This one's job is just to apply more pressure to this one. This is the one that does the work. The reason it's called a dual servo is when you go in reverse, we change and it goes the other way around. So dual means two. This one serves this one going forward, and this one serves this one going in reverse. Dual servo. Okay? Now we also have what's called self-energizing effect. That means that if I were to lock this one in so this can move at the bottom, and we rotate this way, and I push out at the top, when I'm pushing here and rotating this way, it's going to have a tendency, that friction, to pull us in even tighter. Would you agree? When we come over on this side, it's pushing out this way, but we're rotating this way, and the friction is going to try and push this one back in. So on that one we have called a leading trailing system. Okay? And they're not a servo because they're not tied together. Now look at this one. Is this a servo or is it a leading trailing? Leading trailing, because I have a solid pin back there. This one cannot affect this one. You see that? And the leading trailing changes. So we have a leading edge and a following or trailing edge. And when we go backwards, they change places. On a leading trailing, the friction material is the same length from side to side because each shoe stands for itself. On a dual servo, since this one's job is to apply pressure to this one, it's made out of different friction material. It's usually a different thickness and a different length because this job isn't really to stop the car, it's to apply pressure to this one, so it stops it. So if you ever look and your shoes have different length of friction material, the short shoe always goes to the Front. Okay. Okay. That's called the primary. It's just like an election. You have the primary before you have a real election, right? Primary is first. The primary is the first shoe towards the front bumper. Secondary is the rear. Okay. We have a lot of different configurations of this, and we covered them in class. I'm not going to cover them here other than you need to know the differences. All right. So we covered the size of the piston here for the pressure. Now we have another thing that happens. If we have a pickup, let's say Jeff pickup, when he drives that empty, he has very little weight in the back. When you're driving down the road, especially a dirt road, you step on the brakes, you get too much braking in back, it's going to lock the back brakes up, right? So we don't want to lose the back brakes on a corner in the gravel road. And so we've got to do something to change the brake pressure there. Conversely, if we take his truck and we put 1,000 pounds in the back of it, and we're on the same road, and you step on the brakes, now he's got 1,000 pounds more in the back. We want to have more pressure on the back now, right? So the way we change that is called a proportioning valve. With that valve, we change how hard the brakes work, or the application force of the brakes, in proportion to the load on the vehicle. The heavier the load, the more brakes we need. Okay? So a proportioning valve is only used on drum brakes, generally on the rear, okay, and it changes the braking in proportion to the load on the vehicle. Now those proportioning valves can be used on cars, they can be used on trucks.
But generally for the back, right?
Yes, for the back. The next thing they did was they wanted an adjustable proportioning valve. And so they did those, like on the Taurus that we looked at. I don't remember whose that was.
This guy's right.
No, it was Josh's.
Well, we put them on cars and light trucks, clear up through 1 ton. And what they did is they put a sensor on the body, and then we put an arm that came down here to the axle or the wheels. Well, the heavier the weight, the further that's going to pull the back end down towards the ground, and it changes that. So the adjustable proportioning valve is going to change or add more pressure. The more weight we have and the closer that comes together, the higher the pressure is going to be and the more braking we have in the back. So the proportioning valve can be either a fixed or it can be adjustable.
Fixed or adjustable. And it can be on cars.
Yes, it will be on cars, yes.
Will be, yeah, okay.
We saw that for Taurus.
Yeah, we saw it on the Taurus.
For those who enjoy the company of large women.
What are you saying, Doug? Quit picking on my weight.
You're talking about your woman.
Oh!
Okay, so we all right with proportioning valve,
Yes.
metering valve,
Yes.
pressure differential switch.
Just kidding.
Okay, so okay with this, leading trailing brakes,
Yes.
servo,
Yes.
dual servo,
Yes.
self-energizing.
Yes.
Okay, so we're okay with that. So now basically we build a brake system. So we're going to start adding to the brake system. We had enough vehicles that were losing the back traction on the rear wheels, especially trucks, going around corners and in gravel, that the manufacturer said, we're going to fix that. So to fix that, they put a valve going to the line for the rear brakes. Now that valve had what's called an accumulator, which is a spring to accumulate or gather the pressure. And we had to have a solenoid to turn it on and off. So in normal braking, you step on the brakes and there's no difference in the pressure. It's just like regular brakes. But if the rear wheels start to lock up, we want to release the pressure on that brakes so we don't go into a skid. So how are we going to do that? We had to keep track of the speed the wheels turn. The early systems would watch. If you're doing 50 miles an hour and you hit the brakes, we get a signal that we've hit the brakes because it turned the brake lights on. We also send that signal to the computer. So it knows we turned the brakes on. Now it's monitoring the rear wheels. If the rear wheels go from 50 miles an hour to 30 miles an hour just instantly, then it knows we have a problem because it's designed in there for braking. It should slow down at a certain rate. Well, if it happens real fast, that's a red light. It tells us that we are sliding the rear wheels because they stopped.
What happens if you slam on the brakes?
So the fluid goes into the accumulator and lets pressure off.
That's right. So if the rear wheels start to slide, if it recognizes that there's too fast a change in speed, it opens the solenoid, and now the pressure going to the back wheels comes through that solenoid we just opened up into an accumulator and pushes a little valve there, so the pressure's bled off the back. Okay? And it does it just for short periods, like a tenth of a second. So it's going to monitor how fast the wheels turn, and if they slow too fast, it's going to dump the pressure, and if the wheels are still turning too slow, it's going to dump it again. So the customer's going to feel in analog braking like this as it keeps dumping the pressure.
That's analog brakes.
Okay, that's analog brakes. Okay. And that's what it does. It dumps the pressure, and you're going to feel it in your foot because the pressure, instead of being solid, is suctioned off here, and when you do that, you're going to feel a bump in your foot. It changes the pressure, and it takes it in that accumulator. All right? As soon as the wheels are turning the same speed, it closes the solenoid and locks that accumulator off, so now the pressure will maintain in the back brakes. When we take our foot off the brakes, the computer says, okay, we're not on the brakes anymore. I know the accumulator has fluid in it. Okay, so with no brakes, I'm going to open that valve again, and now I have almost no pressure in the brakes, but I do have pressure in the accumulator. Okay, that I bled off. I have a big spring there, so I open that valve, and the spring pushes it out, back up to the master cylinder, and then I close it again. Very simple system, really. You guys okay with that one?
Yeah.
Okay, that is the early analog brakes. Now, to tell how fast the wheels are turning, we had to use a speed sensor. The early ones, we call them wheel speed sensor, but the early ones were put on the differential. Since it was for both rear wheels, we just needed to keep track of how fast the ring gear was turning on the rear wheels, right? If they lock up, it's got to quit turning. So we only have one sensor that goes off from the rear wheel. Now, another thing that they may ask you on a wheel speed or a differential speed sensor is, can it affect transfer case shifting?
Yes.
Yes.
Yes, because if it thinks it's going to tear something up, it's not going to shift. Okay? That speed sensor can be used for our speedometer. Okay, we can take that to tell us how fast the rear wheels are turning. So it can affect the speedometer. The door locks automatically lock when you hit like 7 miles an hour. Okay.
I didn't think about that.
Analog brakes. And it can also affect how the transmission shifts.
Is that the same with the throttle positioning sensor?
No, that thing.
No, that's completely different. Okay. So now we've gone through the early analog brake systems. Now, if we're ready, we're going to take another step. The next step is we wanted to do 4-wheel disc brakes. To do that, instead of just monitoring the one ring gear and one sensor in the back, we put analog brakes on each front wheel. So now we have a speed sensor in front, left, and right, and only one in the back because it affects both rear wheels. So we have 3 speed sensors. And it will kick off both front brakes, or it can do the left or the right independent. And that was easy to do because from the master cylinder, remember we split and go to the left and the right front? We just put a control on each one, but we've got one line going all the way to the back before it splits on the differential. So that was the next step. We had 3 speed sensors. We have analog brakes, left front, right front, and both rear wheels. The step beyond that was we started putting a wheel speed sensor on each rear wheel. So now we have 4 speed sensors. Okay, and I can't tell you which one you're going to have. And on 4, it monitors every wheel, and that has the ability to drop that little accumulator that we put in for both rear wheels. Now we just take a little one and put one for each wheel. So I can do any wheel independent. If the left front's starting to slide, I just open that valve and drop the pressure of the left front. That's the only one. Or the right front. Or the right rear. Whichever one's spinning, we drop the pressure to that wheel. So all we did was made it more individual. And do one wheel at a time. Okay, that's the next step. And the wheel speed sensors take an AC voltage. It's called a sine wave that goes like this. The computer can't read that varying voltage. It reads on or off. So we have to take that varying voltage and change it to a square digital signal that the computer can read. And so all 4 wheels, you're going to have a question on this. They need to show that they're turning the same speed. And that is amplitude, or how high the signal goes, and frequency, how often it occurs. Okay? And it compares all 4 wheels. And if one sensor is starting to go bad, it may not send as high a voltage. They call that amplitude. If the voltage on one wheel isn't as high as the other 3, it gets off far enough, the computer doesn't recognize the sensor's bad because it has a signal. It just recognizes that the signal isn't as strong as it should be, and it will begin to assume that you have a problem. And when it does that, it's going to turn on your light, saying, I'm not exactly sure what's going on here. You're not stepping on the brakes, but they're not reading the same. I don't know what to do, so I'm going to turn a light on the dash telling you I have a problem, I don't know what to do about it.
Figure it out.
Okay, that's for you to figure out. And I'm going to disable the analog so I don't make a mistake. Is that logical?
That's ABS.
Okay. I know I have a problem, I don't know what to do about it, so I'm going to tell you and I'm going to disable the system. That's what it does. Okay? If you remember that, you can work your way through these questions. You know, and they'll make sense to you. At least in my mind they will. All right, are we ready for the next step? Okay. So now we've gone from single or one control on the rear wheels to 3 sensors to 4 sensors and control on the individual wheels. Somebody else thought, you know, we can add traction control to this.
Yeah.
And so to do that, now we have a different kind of accumulator and we have an electric motor. So we run the electric motor and we build pressure up behind this accumulator to gather, hold, accumulate pressure and fluid. We're going to hold that. We're driving down the road, but this accumulator is going to have 2,000 to 3,000 psi on it. It can be as high as 10,000 psi. And it's just going to hold it in reserve. So if we're going down the road and we start to pull up an icy driveway and let's say a rear wheel drive, let's say the right rear wheel starts to spin. The same wheel speed sensors are going to tell us just like that this wheel's spinning, right? We know the wheel's spinning. We have the pressure already from electric motor and it goes to the brake system. So all we have to do is add a solenoid and we open that valve to take the pressure out of here and apply to the right rear brake shoe or drum, disc. And when we apply pressure to that from the brakes, it slows it down, forces the other wheel to turn and keeps it from sliding. That's traction control. And so all we've done is taken the brake system, we've added another accumulator to hold pressure.
That's like 4 now, right? Because then we have all sensors, because you said 1, 2,
Yeah.
3, and then
And it does it the same way as...
my Saturn.
It's almost the same as taking the pressure off from the brakes, but this time we apply it.
in chunks like...
Yes.
Sporadically like that.
And it does it the same thing. Yes, it's gonna bump it up and watch the wheel speed until they're the same, and then it's gonna back off. And so sometimes it'll bump up and back off and bump up.
And it gives you that crazy light with the little tire marks and it's yellow.
Yeah.
It does it on the
I
side.
just turn it off. It's
Okay. Does it make sense on how your traction control works?
Yeah.
We use the brake circuit. It's already there. The lines are there. We know how it works. The sensors are there. All we had to do is add something to build pressure and a way to let that pressure in the line without you touching the brake.
I think that's funny when it's got stuff.
That's traction control. And so, if that makes sense, that on how traction control works, we now have the ability to apply the brakes. We okay with that? All right. Now we're going to take another step. We've already got the speed sensors, we've got the hydraulic brakes, we've got everything on there, and somebody else says, well, we're losing between pushing the brake pedal and doing this and this and this, we're losing too much. So what we're going to do is we're going to go to a drive-by-wire system
Yeah, we are.
because we have everything already in place. So I'm going to put a sensor on the brake pedal. That's going to change the voltage according to how fast and how hard I step on the brake, which tells the computer, and I already have the controls to apply the brakes, right? So all we do now is tell the computer, and the computer applies the brakes for us. It's called drive-by-wire. You don't physically apply the brakes yourself at all. The computer applies the brakes. Okay? Drive-by-wire system. Can you see how we build on it one step at a time? So it wasn't a big step to go from traction control to drive-by-wire, completely computer-controlled brakes.
Big story of
Okay. Now, to do that, you have to build some safety in. Can you imagine the lawsuit that would happen if somebody stepped on the brakes and they locked up and they did a donut and people died out on the freeway? Okay? So, what are we going to do to prevent that?
Limp mode.
We're going to put in what's called redundancy. In other words, we're going to double check everything we do. So if you step on the brakes, I have a pedal position sensor that tells me, but I also have another backup that tells me the same thing. And usually we're going to do it a different way. So one sensor is going to start at 5 volts, and when you step on the brakes, it's going to drop down to near 0, depending on how hard you step on the brakes. The other is going to start at 0. When you step on the brakes, it goes up towards 5. That's called redundancy. And we can calculate when you step on the brakes X amount, this one should drop down to 2 volts, and this one from 5 to 3, and this one should go from 0 to 2, for example. And if they don't match, then we're going to disable the vehicle because we don't want someone to die. So if you're taking the test and they say there's two pedal position sensors on computer controlled braking, that is true. We don't want to do anything that somebody might die from, and so we're always going to have a redundancy or a double check on the system, on everything we do. That's logical, isn't it?
Yeah.
Okay, keep that in mind when they ask you some questions like that. Always got to be a backup. Okay. So now I have analog brakes, we've got traction control, we have drive-by-wire systems. Okay, let's come over here and look at this one again for just a second. Okay, on this one we have the master cylinder, and right here we have the analog brakes. Can you see this controller here?
Yeah.
Now the controller,
Are those the leader screws right there?
okay, this brake system is probably a front rear split. And so we have 2 solenoids, 2 controllers here. And all they are is electric valves that turn on and off. And since the brake fluid comes from the master cylinder through here and then to the front brakes, this basically is a standalone unit. And since it's filled with brake fluid, we have on each side of it, can you see these right here? Bleeder screw. Okay? And because remember, when we have that accumulator that opens to either let fluid out or in, what happens if we have air in there instead of fluid? You're not going to open the valve and get the air out unless you follow a certain procedure, right? So you can bleed the brakes. You can run a quart of brake fluid through this thing and bleed everything, but if this thing still has air behind the accumulator, you still got air in the system, right? And they may work just fine until your anti-locks kick on, and then it fills the system and your brakes are even worse. So what I want to tell you on this, if it has anti-lock brakes, you always follow the manual on bleeding the brakes. There are some that the only way you can bleed the brakes is with a scanner. You go in the brake systems and you tell it that you're bleeding the brakes, and it will tell you push this button and it'll energize this solenoid, and then you bleed this brake, and since it holds it open, it will run the fluid through and push all the air out.
Right.
If you don't open the solenoid, you won't get the air out. So you have to have a scanner. There's others. This one generally does not require a scanner because they have a bleed screw right here on each side to get the air out.
So that would
And
be,
that on
that'd
any-
be an enclosed system with no bleeder valves.
Yeah, so you have to use the scanner. And so we have a bleeder valve, even on the early analog systems where it's only on the rear brakes going to the back. Since we have an accumulator that can be filled with air, which will affect our braking, we have to bleed that anytime it's working. Anytime we change it. Now, if we don't bleed that out and get air in it, we don't have to bleed it again. So most of the time you don't. But if you put a new one on, if the line's been broken, anytime it's full of air, you've got to get it out. Just keep that in mind. If it's got air in, you've got to get it out. If it's a solenoid that only lets it out when it's open, you've got to open the solenoid. Right? Okay, logical to me. So we got to follow the procedure on these. And some of these take a lot of bleeding to get everything through there. Okay, how are we doing so far? It's a pretty quick review, but we doing okay with it?
Yep.
Okay. Now, I want to just show you or review a few of the basic things that you've got to know. I'm not going to cover a whole lot more about on the electronics, because every system's a little bit different. I just covered something. Every system has to have speed sensors. Every system has to have an accumulator. Every system can get air in it. Okay? Hey, Corinne, did you need me?
Yes.
On around here, we're going to finish our review. As part of making sure that our brake systems are okay, we have to verify that our braking components are within specification. So on a rotor, we need to measure a couple of things. We need to measure the thickness of the rotor and make sure that it's within specifications, because it takes kinetic energy and changes it to heat energy. That heat comes in here and is dissipated. This is kind of like a fan to pull air through it. If we don't have enough metal to absorb the heat, then the fluid can boil and somebody can die. Okay? So checking the thickness is extremely important. Now, when we clamp on here and this is spinning around, we can have some problems that the driver will feel. First of all, if this thing's moving back and forth like this, it's called lateral runout, side to side. The caliper sits over here, and as it moves, the caliper has to move back and forth with it. Can you see that? Mm-hmm. For the caliper to move, on this one, it sits on these pins. These are called, this one is called a sliding caliper. These pins have to be free. If they are not, and the caliper can't move, it's going to hang up and burn one brake shoe up sooner than the other because it can't completely release. The piston is on one side. For the piston to push and apply pressure, it has to hold equal pressure on the back side to hold it. So we can apply a lot of pressure, and when we release, remember how a piston on the caliper releases? Square cut O-ring pulls it back. Well, this side has been applied with the same pressure, and it has to relax too on these pins. And if the pins are stuck, it can't relax on one side, and it's going to stay applied on the back side. So we've got to make sure the pins move. We got to make sure our thickness is okay. And then we have to check what's called parallelism, meaning that this one piece of steel isn't going to be the same all the way around it. It's not going to wear the same. It's going to have different spots of the metal that are a little softer, a little harder than other spots. When that happens, if it wears a little more here than it does over here, we clamp on it. When it goes through the narrow spot, the piston moves in, and then we hit a wide spot, and the metal physically forces that piston back out. The piston's going to push the brake fluid back up the master cylinder. You're going to feel that in your foot. When it goes through a wider spot, it pushes the fluid back. Okay? So you're going to feel that in your foot. If it's lateral and moves back and forth like this, you generally feel it more in your steering wheel. When you're braking. Yes. So make sure you always check it for thickness within specification, parallelism, lateral run out. We can check with a dial indicator. We can put on here and turn it and check the movement on it. Okay, now let's come back and look at this one.
Oh, look at that, baby pad.
Okay.
Put in there wrong.
Holy crap! Oh yeah, that was your.
Somebody just had this apart and they were ready to put it back together, and I stopped them and I said, "Don't! I want this for my class." It's upside down and backwards.
It was some student.
High school stuff.
Upside down and backwards, huh?
Upside down and backwards.
Nice.
Now, just out of the conversation, can that happen, Dusty?
Yes, Pappy.
Apparently.
That one in for
Yeah. She did one this last year, if you remember, where the
you. The
pad was put in upside down,
yeah.
backwards, so it's metal to metal, and it wore the wrong.
Yeah, I
So
gave you
it
that.
happens. Okay, we have that. Okay, this one is a caliper in back, so this one is thinner. Why would this rotor be thinner than that one?
So the
That's braking.
The front does
70%.
of the braking, so this doesn't get near as hot, so the pads aren't as big, the rotor's not as thick. That's logical, right? Okay. We need to make sure these are correct. The pads, we can check the thickness of these. There's a gauge that measures in 30 of an inch. And for safety inspection, if they get below 2/32, they need to be replaced.
Say that
Okay?
again. 2 to 3 seconds.
2/32 of an inch. Then they need to be replaced. So we got to check this the same way we did the front. Now, on the rear calipers, on some of the cars, we have to have a park brake. Remember, we do not call it emergency brake.
Park.
We're not going to tell the customer it's for an emergency. It's to hold it when it's in park. It does help us if we lose all of our brakes because it gives us a mechanical system. But we're not going to tell them it's emergency because that's not what it's designed for. We have to be able to mechanically apply the brakes. It's usually on the rear shoes. Subaru, there are a few exceptions that does it on the front, but most of the time it's on the back. Okay. On this one, you can see we have a cable coming right here to the caliper. The caliper is going to pull an arm, and the arm is going to twist and physically turn this piston out to mechanically apply the brakes. It's got like a little screw in there that this cable pulls. Okay? Or the cable would pull if it wasn't broke off. Now, when you work on these and you apply the park brake, and it turns this inside this screw, it's going to push this out to compensate for wear, so our park brake still works. When you go to put new pads on there, this piston's going to be all the way out. So you have to be able to turn it back in. If you look here, there's a cutout right here and right here. There's a specialty tool we put in there, and we turn that back in against the threads to move the piston all the way back in. Okay? And you're not going to get the new pads on there if you don't turn the piston back in. When you get done, on the back, right here, there's a little pin. Can you see it? That little pin has to go in one of these grooves here to keep this from turning on there. So when you change these kind of pads, brake pads, and you put them on, you have to make sure that this is lined up so that goes in one of these grooves. So it's going to sit just like this, right in there, and it's got to fit on that little clip right there. Okay, always inspect the wear. Can you see the difference in the amount of wear from one pad to the other one?
I'm failing those brakes.
Okay, so if you're doing an inspection on somebody's brakes, you can't just take a flashlight and look in here and say they're okay, because on this one,
about a 1.
yeah, this one would be below
1/3
specifications. These brakes need to be done. Okay, they do
That
not
one's
pass.
probably about a 3 or 4,
2.
This one's probably about 2.
right around 2.
Yeah. Now, on this one, we have this little piece here. Does anybody know what that is?
Anti-rattle indicator.
It's a wear indicator. And what it does, when it sits on here like this and the pad gets worn enough, this will start to scrape
Hey,
right here on the rotor.
Change me.
And as it does, it's going to start vibrating or squealing. Okay, some
That's
people call
really-
them a squealer. And it's going to sit here and squeal like this. Okay, as it rotates around. When you step on the brake, it pushes in tight and the squeal goes away. So if a customer comes in and they have a noise or a squealing noise on the brakes, you step on them and the squeal goes away, it's worn out. It's telling you it needs to be changed. Okay, and that's what this is for. Now, we have this piece right here. You guys see this one?
Anti-rattle.
One top and bottom. And it also has, see this piece right here? A lot of different variations for this. But when this pad sits on here like this and the caliper pulls away, it can rattle and create a noise. Customers don't like that, you know, and especially when you're by another building and it reflects a sound back. So in my experience, about 90% of the complaints on this are when I'm pulling through McDonald's, you know, I got my window down and I'm pulling up there to make my order and I can hear my brakes
Grinding.
vibrating or squealing or something. That's when they hear it.
Or when you're
Okay?
going 30
And
miles
so
an
to
hour.
keep this from vibrating or rattling, we're going to put this clip, okay? This clip goes on and you can see how it pushes on the end right there when this goes up in place. Can you see it push there?
Yep.
And down there, see it? And since it's pushing on it, it keeps it from rattling. So it's called an anti-rattle clip. And some people will ask you, does it have to be there for the brakes to function? No, it doesn't. But if it's not there, the customer is going to complain about a squealing noise or vibration, something like that. And you should replace the anti-rattle clips every time you do the brake pads.
They should come in the kit.
Generally, they come in the kit, unless you buy real inexpensive brakes.
If you buy the cheap house brand brakes, they don't.
Okay.
Especially if it's your house brand.
Our house brand carries them. You had to open every box and put packages in every box.
Okay, we'll let those guys put this back together.
No, you should have put it
All right.
the way it had it.
Unless you get organics.
How are we doing on this? Do you have any questions on, this is just an overall brake from the pedal all the way out to the rear wheels and a little bit on analog brakes. Did it help? Yes. Any questions for me? Okay, good luck on your test tomorrow. We're done for today.